Hi, the example for dispersed Poisson model. So again, we use the number of plant species in the 30 the Galapagos Islands. So the number of species is a count. So this is Y, and the 30 Galapagos Islands. So this is the observations. So N is equal to 30. And we have 5 predictors and 6 parameters. So in our notation, P is equal to 6. And the number of variables is 5. And okay, so actually in section 5.1, we have seen that even though we have the 5 predictors, still the model isn't really good enough to be accepted against the saturated model. So we have to improve the situation. Okay, so first we check the outliers, and also we want to check if the dispersion model is appropriate. So the outliers that we can use a half normal QQ plot, and here the half normal QQ plot, and this is the theoretical quantile, and this is actually the residual, the sample residuals. And you can see that there are no outliers. So this 11th observation has largest error, but it's really the error size is really close to other observations. So no outliers. So this is not the reason for the over dispersion. We will see later. And also that we want to see if the dispersion model is appropriate. So if dispersion model is true, even though the distribution is not clear, the variance of y is equal to phi times EY. So if we plot maybe the estimated the expectation of y and the estimated variance of y, then that should be on the same line with the positive slope, the phi. So basically the variance of y is equal to phi times EY. So it should be like this. And we cannot really observe the variance of y hat and the expectation of y hat itself, but we use just the approximate value, the mu I hat, and the yi minus mu I hat, the square of that. Then we have to have this situation. Yeah, but usually the x and the y are heavy-tailed, especially the y is count. So usually it's skewed to the right. So we take the logarithm. So we think about the log of y and log of x. So that becomes log of y is equal to the log of phi plus log of y, log of x, sorry. Yeah, and so we described the model here. So this is basically the log of expectation of y, and the y value. So the horizontal, sorry, the vertical axis is the log of y, or log of the variance. So we have to have the relationship, the log of y is equal to log of phi plus log of x. And I wrote the 3 lines. So the black line is actually the log of y is equal to log of x. So this is just diagonal line. We have just a different scale here, 2.5 to 6 and 0 to 10. But this is basically the line with the slope 1, and it goes through the origin. And the second graph is the log of y is equal to the 2 plus log of x I draw. And another one is log of y is equal to 4 plus log of x. If the observations are follows either of these lines, then the model, the dispersion model, is appropriate. And we can roughly say that these observations have some positive linear trend. So probably this one is closest. But anyway, so maybe at least it is not too bad to assume the dispersed, the Poisson model. And actually the estimated log of phi is actually estimated phi is about 31 that we will see later. So actually the log of phi is almost 4, maybe 3.5 or something. So it's actually the closer to this line, and it's not really intuitive. But remember that we take the logarithm. So before taking logarithm, these observations are really large in terms of x values or y values. So actually, before taking log, so these observations have higher influence. So the estimated phi is pretty large, e to the power 3.5 or something. So the overall, it's not too bad to assume the dispersed, the Poisson model. And here is the code for the previous two figures. The first one is half normal QQ plot, and the other one is just a plot of the fitted value, the log of fitted value and log of the squared, the y minus the fitted value. And the AB line that you can see, this is y is equal to x. In general, this is y is equal to 0 plus 1x. And this is the 2 plus 1x, and this is 4 plus 1x. Yeah, and now that we estimate phi, so at first we calculate the degrees of freedom, the number of observations 30, and the number of variables, actually the 5 variables. So including intercept, we have the 6 observations. So degrees of freedom is 24. So we take the sum of the squared, the residuals, so that is this one. Then take square, take summation, yeah, and then divide by the degrees of freedom, 24. Then we get 31.7. So this is estimated phi. So estimated phi should be around 1 if the Poisson model is correct. So it deviates a lot from the Poisson model. So it's beneficial to introduce this parameter phi. And here is the summary of the Poisson regression model with dispersion parameter. And actually the estimate are the same as the previous section, but the standard errors are different. So this gets much larger. You can compare. So as a result, you can see different z values. Basically, this becomes much smaller, but still these are significant. Maybe the nearest and the SCRUZ. So these two variable becomes insignificant from the previous one. So last time, every variables are really significant. The p-value is all less than 0.0001, but this time these are not the significant variables. So we have our conclusion has slightly changed. Yeah, and the other quantities are the same. So still these are the same. So we don't really re-estimate the model, but we just adjust the standard error. So we adjust the conclusion or p-values. And another way to do the same thing is using this quasi-Poisson option. Then you can just use the GLM function, and it generates exactly the same output as the previous page. So now the F-test. So we can do the test by z statistic and the p-value that we have seen the p-values in the 2 slides ago. But the p-value is based on the normal approximation of the estimate, and that isn't really good. So that is just approximately normal because we don't really, we cannot really assume anything. So if sample size is really large, then we can rely on the asymptotics of the MLE, then we get the normality. But the convergence to normality is not really fast. So using F-test is more accurate than using the Z statistic. Yeah, so drop one function we use, then we can test, for example, the full model and the full model minus the area. So the full model is the mu is equal to the beta 1 times beta naught plus beta 1 times area, beta 2 times elevation, and beta 3 times nearest, and beta 4 times S screws, and the plus beta 5 times adjustment. But here, the elevation, so here, the second model is area. So we don't have this term. We don't have this term. So if we drop this, it's significantly worse or not. And that test was done with this. Yeah, so p-value is 0.00047. So it's probably not much different from the previous one. Here, maybe slightly smaller, the 000, it's 10 to the power 5. So 1, 2, 3, 4, 5, maybe. 1, 2, 3, 4, 5, yeah. And this amount, so 0.00008, so that becomes 0.00047. So it's actually a little larger, but it's similar. And especially these ones are similar. But it's considered that F-test is more accurate. Yeah, so the F-test still rely on asymptotic distribution. So yeah, but this is a little more accurate. Yeah, then on a note on the F-test. So what's the F-test? So F-test is basically the chi-square test, but it's adjusted by something. So originally we have this term, the difference in deviations. Then we divide by, yeah, so this follows chi-square distribution. So this follows chi-square distribution with the DFS minus DFL. DFS and DFL are degrees of freedom for these two models. But here we have one more uncertainty, that is the phi hat. And the phi hat has the degrees of freedom n minus p, because we have n observations and the p parameters. So it's estimated with df n minus p. And so we take the ratio between this. So phi is large, then every variance is inflated, so that we adjust this, but this follows the chi-square distribution with dfn minus p, and the numerator also chi-square. So we take the ratio to get the F distribution. So in the previous case, what's the F statistic? So think about this one. So how this was obtained? So basically, this is the difference in deviance. So 2000, sorry, the 1204.35 minus 716 plus 85, and divided by the degrees of freedom. But the area is just one parameter, so this is 1. Maybe to be exact, the larger model has the degrees of freedom, the 24, and smaller model is 25. So maybe I would say that's the 25 minus 24. But anyway, so the difference in parameter is 1. So this is divided by 1. Then the phi hat was 31.7. But actually this does not, so this should be the 13.3217. But actually, this does not become this number, like the 15.7 or 8. So slightly different. And yeah, when I see that, result, probably this quantity was estimated as different number. So about 29.8 or something. So I don't know why this discrepancy appears, but probably the estimate for phi is different, because this is not just a linear model, but we have the link function and so on. So we did some adjustment to calculate the optimal phi hat. So it doesn't exactly coincide with our output in the previous page, but basically the f is calculated in this way. So let me know if you exactly figured out how are calculated the f statistic.